Well, good afternoon, everybody. It's my pleasure to introduce our today's speaker, Sophie Spirkl. She did her PhD in 2018 in Princeton under supervision of Maria Chudnovsky and Alex Seymour. And then she had postdoc positions at Rutgers and again in Princeton. And from last year, she's assistant professor at University of Waterloo. Yeah, and today she's going to talk about new results on polynomial chi-boundedness. Please.
Thank you. Thank you for the introduction. Thank you for inviting me. And thanks for coming to my talk. So throughout this talk, I'm happy for anyone to ask questions either by unmuting or by putting them in the chat, whatever works for you. And I will tell you about polynomial chi-boundedness, and let me start slowly. So I care about induced subgraphs. If you have two graphs, then induced subgraphs is a containment relation where you can only delete vertices. So in particular, here's my favorite example. If you look at this graph G, then by deleting this top vertex, you get this induced subgraph. But there's no way to get this one without deleting edges by themselves. And so, that raises the question, what can we say about H-free graphs, where H-free always throughout the talk means does not contain H as an induced subgraph. And here for chi-boundedness, we're really asking about coloring. So as you probably all know, the chromatic number of a graph is the smallest k such that we can assign to each vertex a color between 1 and k with the property that adjacent vertices get different colors. And the clique number of a graph is the size of a largest clique, where a clique is a set of vertices that are all pairwise adjacent. And the whole point of chi-boundedness is that for every graph, its chromatic number is at least its clique number, because if you have a clique, all the vertices get different colors. And chi-boundedness asks, when is there any kind of bound in the other direction? And so more precisely, we say that a class of graphs is chi-bounded if there is some function that gives us a bound in the other direction, bounding chromatic number by a function of the clique number. And as you can verify if you think about it for a second, this only makes sense if the class C is an infinite class of graphs, because for any finite class, you can always find a function that works. And we add the word polynomial if we can choose the function f to be a polynomial. And usually in this context, we ask that C is hereditary, which means closed undertaking induced subgraphs, to avoid some weird examples. And so, for example, when you pick f of x to be x and you look at a hereditary class of graphs, you will get perfect graphs. Sorry. And since chromatic number is at least clique number, this is somehow the smallest chi-bounding function you could imagine, and every other chi-bounding function gives you a generalization of perfect graphs. So we ask, for which graphs H are H-free graphs chi-bounded? And there's a famous conjecture of Jaffish and Seymour saying this is true when H is a tree, where a tree is a connected graph with no cycles. And in fact, this is sort of tight in the sense that it may be true for all forests, which are just graphs without cycles, and it's definitely not true if H has a cycle. There's an old construction due to Erdős of random graphs that have large girth, and so in particular they have clique number 2, but also have large chromatic number. And so that shows that for any cycle and for any graph containing a cycle, H-free graphs are not chi-bounded. And this conjecture is known for several kinds of trees, and I drew a few examples for you here that kind of give some of the most interesting classes of trees that this is currently known for, but in general, it's still open. And for this talk, we're interested in polynomial chi-boundedness, whereas the previous slide was just about normal chi-boundedness. And there's this very striking and slightly frustrating conjecture of Esperet, which says that maybe in hereditary classes of graphs, chi-boundedness and polynomial chi-boundedness are the same phenomenon. This conjecture seems really unlikely to be true, right? Because polynomial chi-boundedness is somehow something that sounds so much stronger than just normal chi-boundedness. But so far, nobody's found a counterexample to this. And the other thing I should say about polynomial chi-boundedness is we care about it in part because it relates to the Edersheimel conjecture. So the Edersheimel conjecture is another conjecture that says something about how our H-free graphs differ from random graphs, from general graphs, by saying for every graph H, if you exclude it as an induced subgraph, there is a constant that depends only on H, such that if you have an H-free graph on n vertices, then it has a clique or stable set of polynomial size of size n to the c. And again, if you go back and think about what happens if I don't know that G is H-free, then I can only guarantee a clique or stable set that is logarithmic in size. So this is a conjecture then would describe how H-free graphs are really very strikingly different from random graphs. And it's not hard to see that polynomial chi-boundedness implies that the Edersheimel conjecture holds for a class of graphs, because if you know that the chromatic number is bounded by the clique number to the k for some k, then you can do the usual, a coloring is a partition into stable sets. So you get a stable set, that's what alpha denotes, the size of a largest stable set of size at least, number of vertices divided by chromatic number, that's just true in all graphs, which here, if we know polynomial chi-boundedness is at least this. And then you can tell that alpha times omega to the k is at least n. So by doing a geometric mean, you can tell that alpha or omega is at least n to the 1 over k plus 1. Right, so very easily, the polynomial chi-boundedness implies the Edersheimel conjecture. The reverse is not true, and in fact, for example, we know the Edersheimel conjecture for C5 of 5 vertex cycle now, but excluding any cycle doesn't even make you chi-bounded. So this is not in any way an equivalence, but it happens that the smallest open case for the Edersheimel conjecture is a 5 vertex path, which in particular is a tree for which we know that excluding it makes you chi-bounded. So if only we could get P5 free graphs to be polynomially chi-bounded, we would have proved the very next case of the Edersheimel conjecture, which would be really nice if we could do it, but currently we can't. But so this is part of what motivated this. Can we get anywhere for P5? And I will show you lots of results that don't quite get there for P5. So what do we know about polynomial chi-boundedness? From what I've told you so far, we can only hope that it's true for H-free graphs if H is a tree or a forest. And also, since P5 is still open, there should be a forest that doesn't contain P5 as an induced subgraph. So that narrows down the options a little bit. It's not hard to see that if you exclude K1T, which is this T plus 1 vertex graph, you get polynomial chi-boundedness, because when you look at a vertex, its degree is bounded by something like omega to the t, since you don't have a clique of size omega and a stable set of size t among its neighbors. If you look at P4, which is a 4 vertex path, excluding that makes you chi-bounded because P4 free graphs are perfect. And one of the first results that was slightly harder to prove is if you exclude SK2, which means S disjoint copies of K2, which is a graph with one edge, then Wagon proved that excluding that makes you polynomially chi-bounded as well. And so very recently, for people from Georgia Tech, proved that if you exclude this graph, which you can think of as sort of a mixture of K1T and P4 at the same time, then excluding this not only makes you polynomially chi-bounded, but they also get a bound on the chromatic number that's very close to being optimal for excluding this graph as an induced subgraph. And in general, for T at least 5, one of the important open cases is what happens if we exclude a T vertex path. And for PT-free graphs in general, we know that they are chi-bounded. In fact, the first paper by Jafresh that introduced chi-boundedness as a concept proved it for excluding a T vertex path. That's one of the first and easiest proofs about chi-boundedness, but it's also an exponential bound. So this is sort of the most interesting open case, especially for 5, but also for longer paths. So here's what we proved, a series of results that don't prove the thing for P5. First, I showed you on the previous slide that we can exclude one star, but in fact, we can exclude a number of copies of a star. And the fact that this even needs to be proved might be surprising, because for normal chi-boundedness, if the result is true for H and it's true for H prime, then it's also true if you exclude their disjoint union. But for polynomial chi-boundedness, that's not immediate. In fact, we don't know if that's true in general. So I will show you this proof, but before showing you this proof, I wanted to tell you why we actually need to prove this. Because if you've worked with normal chi-boundedness before, you would think this is obvious. And then the next thing we proved is excluding a doubled star. A doubled star is just an edge with 2 stars on either side. And the way to think about this maybe is this is what every P5 free tree looks like. So as far as trees go, since we can't do P5, this is the best we will do for trees. And then for P5, we showed a bound that is not polynomial, but at least sub-exponential. And unfortunately, it doesn't tell us anything new about Erdős-Heinel. But it's, closer to polynomial than we were before, in some sense. So, yeah, and if there are questions, ask me questions. I'm happy to answer them throughout or at the end or whenever you'd like. And if not, we're going into the part of the talk where I tell you proofs of things. So the proof for a disjoint union of stars, which I'll tell you first, is actually a bit stronger. It tells you that if you have any graph H and you take the disjoint union with a star, then if H-free graphs are polynomially chi-bounded, so are graphs you get that are the disjoint union of H and a star free. And this slide contains the basic idea, and then I'll make it more precise on the next few slides. So we assume some chi-bounding function where I'm assuming it is of this form, which is not maybe entirely honest, but let's say for H-free graphs G prime. And then our plan is to do the following. We look at a vertex with many neighbors, which we can assume exists because of degree is bounded, so it's chromatic number. And then we partition the non-neighbors of V into 2 kinds of vertices, the ones that have many non-neighbors among the neighbors of V. And, if somebody has many non-neighbors in here, then those non-neighbors contain a stable set of size T, and so you would hope to find a star with no neighbors here. That's not quite precise, but that's the rough idea. If you have many non-neighbors, then maybe you're close to not containing H, because this part is close to containing a star disjoint from you. And on the other hand, there are people with few non-neighbors. And the way to deal with them is, well, if you have many, many edges to here, then not both sets can contain a big clique. And so if one of them has small clique number, we can apply induction and get somewhere. So how do we actually do this? On the next slide, we're going to look at this set a bit more carefully. So picture X as the neighbors of V. And what we're going to do in X is the following. We're going to say, take a largest clique in X, call it K1, put it aside, and what remains, take the largest clique, call it K2, put it aside, and what remains, take the largest clique, call it K3, put it aside, and so on, for some time where I'll tell you what N is later. But take some large number of cliques that are disjoint, but we don't know the edges between them, and put them all aside as one subset of X. And then the rest has clique numbers, some number K, where each of the cliques K1 up to Kn has size at least K, because we always took the largest clique. And this will help us make more precise what we mean by neighbors and non-neighbors, many neighbors and non-neighbors in X. For the remaining vertices, we can partition them into Y, which are vertices that have clique number K less than omega of G, and Z, vertices that have at least N, where N, remember, is the number of these cliques over omega of G non-neighbors in this union, because, put each vertex with that many non-neighbors in the union of K1 up to Kn into Z, and then look at what remains. And what remains, if you had a clique of size bigger than that, then each vertex in that clique would have very few non-neighbors in K1 up through Kn. In fact, this is not enough to have one non-neighbor in each of them.
Oh, sorry, can you explain the definition of Y? So you take all vertices little y, and what's the condition? A bit lost here.
Yes, thank you. Into Z, put the ones that have at least this many non-neighbors in the union of K1 up to Kn, and then Y is the remainder. And if you think of the remainder, and if you think maybe there's a clique here of size bigger than omega of G minus K, then for each of them, you can look at which cliques it has a non-neighbor in. And together, these vertices will have a non-neighbor in at most omega of G times something less than this, because each of them has less than N over omega of G. So in total, the number of these sets where any vertex in my new clique, say Y prime, has a non-neighbor is less than N. So Y prime has to be complete to one of these cliques. And since each of them has size at least K, we have a clique, for example, maybe this one of size more than omega of G, a contradiction. All right, this partition makes more sense if we put Z aside first and then look at what remains. And in what remains, we notice we can't have a big clique. Yes, thank you for clarifying that. I think saying it that way around hopefully made more sense. So let me show you again what this looks like in the picture with V and its neighbors. So we have V here and its neighbors, and we've done this take a max clique, put it aside procedure in the set of neighbors of V. And now what remains, as we said before, what remains can be partitioned into y, something where the clique number went down to omega of g minus k, where k is the clique number of what remains here in x, and into vertices with at least n over omega of g non-neighbors among this set. So let me now choose n to be omega times the Ramsey number of omega of g and t, which is just what we need to ensure that for vertex here, its non-neighbors there have a stable set of size t. And then let me say for each stable set of size t here, put its non-neighbors into their own set. And then we know that Zen that we had previously put aside, every vertex of that set Zen fits into one of our sets Z1 up to ZQ. And these numbers are huge but polynomial because this is something like omega to the t. And so this is omega to the t plus 1. And therefore Q, the number of choices of Z we need, is something like this, where this is omega to the t plus 1. So it's omega to the some polynomial in t, which is not nice, but polynomial. Right, so what have we done for each of these? We now have t, a stable set of size t of common non-neighbors of Zi. So this set is actually H-free. Right, we took the vertices that had many non-neighbors in K1 up to Kn, and we grouped them by which non-neighbors, but by choosing the grouping along according to a stable set of size t, we made it so that the number of groups required was polynomial. And now each group itself has among their common non-neighbors a K1t, and so it's H-free. So we get a bound on the chromatic number that I've written down here, which is, this is what Q is, the number of sets that go here, and each of them has chromatic number at most omega to the r, because that's what's true for H-free graphs. And this is what we get for X star, because that's just the number of vertices that live there. And now here we have a set of clique number k and a set of clique number omega of g minus k. So applying induction, we get for some k between 1 and omega minus 1, the sum of f of k and f of omega minus k. And if you think about the sum and think of f of g being f of k being a polynomial, then this is a sum that is of a convex function. So you would think the max would be attained at one of the ends of the interval. And at the ends of the interval, k is 1 or omega minus 1. So this is roughly f of 1 plus f of omega minus 1, which is good for us because now we have a bunch of stuff that's polynomial in omega plus f of omega minus 1. So if f of omega is roughly this stuff times omega, then we're in good shape.
Can I ask you another question? So in this proof, V is any vertex, or you need to choose it like carefully?
You need to be slightly careful to make it have huge degrees so that we don't run out of stuff here. We're using that the clique number here is at least 1, right? If it went down to 0, we would be in trouble.
I see, okay, thanks.
Yes, good question. We choose it to have enough neighbors that during this procedure, the number of times we need to do it doesn't run out all of these neighbors. And that's the only place where we need to be careful. We can certainly assume there's a vertex of large degree. That's all we need. So yeah, we get a copy of this if we're not chi-bounded, basically wherever we want it. Okay. Now, that was the first proof of this talk. The second one is the proof for P5, and I'm gonna tell you how to get for P5 free graphs this chi-binding function. And to show you this proof, the first question you might have is, how does this kind of function even come about? So let me first tell you where that function comes from, and then we will show how to prove the kind of recursion we need for this function. So during the proof, we're assuming we have a graph with clique number k, and we're assuming that there's a function f such that for induced subgraphs h of g, if their clique number went down, then their chromatic number is bounded by f of their clique number. So we're proving it by induction on clique number. And now, what kind of recursion would f need to satisfy in order to get out a bound that looks kind of like this? As it turns out, proving this kind of bound will work. So we'll prove that the chromatic number of g is at most f of k minus 1 plus k plus 2 f of k over 2 rounded down. And that gives you a bound that is roughly omega to the log omega, because you can say if we have this kind of recursion, then let's apply it k over 2 times to say, at each step, this goes k minus 1, k minus 2, k minus 3, and so on until it's actually down to k over 2. And at each step, we pick up roughly k terms that look like this. So by doing it k over 2 times, we figure out that f of k is roughly k squared times f of k over 2. And now let's look at this recursion, and to go from k over 2 to a constant, we need to go to half the previous number, a logarithmic number of times. So by applying this recursion repeatedly, we get this to be f of 1, or probably f of 2 is more reasonable. And we do log k steps, each time picking up a factor that's roughly k squared. So we end up at roughly k to the log 2k. And this was the world's least honest analysis of a recursion, but that's where that function comes from. And despite the lack of honesty, I think hopefully you can believe that this is sort of the order of magnitude you get from this kind of recursion. All right, so here we want to prove this kind of recursion, which means, we want one thing with clique number 1 smaller, so like the neighborhood of a vertex. And then we're allowed a bunch of sets where the clique number went down to half. And there are 2 steps that are kind of similar, but also kind of not. And before I start doing the steps, let me give you some intuition of what P5 free graphs do. First, there's a technique that's very common and, not hard to show once you think about it for a second, which is this. If you have a connected set S and you have a vertex outside S with both a neighbor and a non-neighbor in S, then you can find a 3-edge path starting at V going into S, because you look at its neighbors and its non-neighbors and you say S is connected, so there's an edge between them. So that's helpful. And so let's call V mixed on S if it has a neighbor and a non-neighbor in S. Then if we're in a P5 free graph, we can look at a cut set, which is just a set whose removal disconnects the graph. And if we look at a minimal cut set, then where no subset of it, say, is a cut set, then every vertex in it will have a neighbor in every component we get from deleting the cut set. Because if there's a vertex that has no neighbor in one component, then he's not actually helping us disconnect the graph. He didn't need to be in the cut set. So what does that mean? Well, it means that if we have a cut set and look at a vertex V in it, then it will have a neighbor in every component we get after deleting X. But if it was mixed on 2 components, we would get P5. So X is complete, meaning adjacent to every vertex in all but one component. So that's our main power. When we look at cut sets and P5 free graphs, oftentimes many vertices are complete to components we get after deleting the cut set. Okay, so here's the first step of the proof. If we have a P5 free graph and we can assume it's connected by induction on number of vertices, say, and we pick F, something that works for clique number 1 less, then let's first prove that for a cut set of G, the chromatic number of the graph having deleted that cut set is at most this, which is not quite the recursion on the previous slide. There will plus 2 here, but also we're deleting a cut set now. So you can think of this as showing that every cut set has large chromatic number, because if we get a cut set of small chromatic number and we know this statement, then we have proved the recursion we want. All right, how do we prove this? Well, we can assume the cut set is minimal because this only gets worse for us if we kick vertices out of the cut set. So let me look at a minimal cut set. And here's X. And now let me look at what happens in the rest of the graph. Let's pick a vertex in X, say V, and then since X is a cut set, it has neighbors and components in every component we get from removing X. So if I look at any specific component, then V also has a neighbor somehow not there. And to prove this, since X is a cut set, it's enough to prove it for every component separately. So let's look at one component, look at V and its neighbors, and look at what happens to this component after deleting the neighbors of V. And so after deleting the neighbors of V from that component, it might just be that the neighbors of V are everything, but then that component has clique number at most k-1 because V is adjacent to everyone, so we're happy. So we can assume there are components that survive, and let's split them into those with chromatic number more than f of k over 2 and at most f of k over 2. And so again, if these guys don't exist, we're happy because here we have f of k-1 and here we have f of k over 2, and that's again what we wanted. So our main goal now is to get rid of these guys. How do we do that? Well, I redrawn this picture, but let me go once more to this. First, notice that if we look at this component and look at vertices with a neighbor in it, they can't be mixed on this component because V has a neighbor somewhere outside, which has a neighbor here because those are the neighbors of V. And if this vertex was mixed on this component, we would get P5. So in fact, for each component Ri, the set of neighbors it has among the neighbors of V, say Yi, is complete to Ri. And so let's think a bit more about these sets. One thing that's helpful is that if we have a vertex with a neighbor in R1 but not R2, and a vertex with a neighbor in R2 but not R1, they have to be adjacent. Because if they're not adjacent, you get exactly this P5 after all. So, right, let's use that to our advantage. We also know that these have chromatic number more than k over 2, so there's a clique of size more than k over 2 in each of these by induction, which means that since these are all adjacent to every vertex of R, Yi has no clique of size k over 2, so the clique number of Yi is less than k over 2. And let's look at the set Y, that's the union of all the Yi. And I claim that that union has small chromatic number because we know each of these sets individually has small chromatic number because it has small clique number. And now we say, let's look at all of Y and pick a minimal set of indices such that the y's corresponding to those indices, their union is already all of y. And the point of that is that when we do that, each index we kept will be needed for some reason. So for each index we kept, there will be a vertex corresponding to that index and none of the others we kept. But I just showed you that if we have two vertices that correspond to different indices, but don't have a common index, then they're adjacent. So the set of indices we kept. If we pick one representative for each of them in such a way that no two representatives, that each representative has a private set R it goes to, it, those representatives form a clique. And therefore, we must be able to cover all of y with at most k-1 of these sets yi, because there can't be a clique of size k here since v is adjacent to all of them. Okay, so what have we done so far? We looked at X, the cut set, we looked at any vertex of it and its neighbors. We split the components we get after deleting those neighbors as well into those with big chromatic number and the ones with small chromatic number. And we showed that for the ones with big chromatic number, their neighbors among the neighbors of V, the set Y, has somewhat small chromatic number, at most does. How does that help? It helps as follows. We're now going to color, and the colors here, red, green, and yellow, are meant to convey where we reuse the same colors. Here are components of small chromatic number, and so we just use their small chromatic number to color them. And they could have neighbors all over the place among the neighbors of V, so we better not reuse those colors. These components, we don't know that they have small chromatic number, but we know that this side was connected, so there is at least one vertex here adjacent to every vertex in Ri, so at least we can color them with f of k-1. And let's also color this stuff, which is the neighbors of V that aren't in any of the Y sets, with f of k-1, and there are no neighbors from here to there, so that's fair. We can reuse those colors. And then the last thing we need to do is color the set Y, and we just showed on the previous slide that the set Y has small chromatic number. So that works. It's possibly slightly mysterious why we did this, but it shows that cut sets have big chromatic number, and it shows some of the main tools we have, right? We know that if something has big chromatic number, at least the things complete to it have kind of small chromatic number. And we showed that in this setting, neighbor sets can't be that wild. They have to somehow at least be covered with a small number of sets. So that's the first half. Let's go to the second half. So for the second half, we now have a +2 here to play with, which tells us, since we just proved that stuff not on the cut set has chromatic number, at most this without the +2, that each cut set has size more than 2 f of k/2. And there's one immediate thing we can say about this, which is there are no two disjoint cliques of size more than k/2 with no edges between them. Because if there are, here they are, and there has to be a cut set separating them because there are no edges between them. So certainly all the rest of the graph is a cut set separating them. But then there's a minimal cut set separating them. And as we discovered, when there's a cut set, no vertex in the cut set can be mixed on both sides. So some vertices in the cut set are complete to the left and some are complete to the right. But this had size k/2 and so did this. So here we have at most twice f of k over 2. So that's odd, right? We can't have two even medium big cliques with no edges between them. Let's use this fact. And this looks like a mess, but let me tell you what's going on. Again, we're going to start with a vertex and we're going to look at its neighbors, and that's one of the cut sets we'll look at. And we can assume that it has big chromatic number and in particular contains a clique of size more than k over 2. And then the rest, we're going to pick a special set Y with the following properties. We want it to be a set Y such that after we delete it, there is a component of G with both Y and the neighbors of A deleted, such that Y is complete to C, meaning every vertex of C is adjacent to every vertex of Y, and C has large chromatic number. And we can do this because the empty set works for Y. We can assume that certainly the right-hand side of the picture has chromatic number, at least f of k over 2, otherwise we're done immediately. So we can pick such a set Y, and as it turns out, by picking it to be maximal, meaning just maximal with respect to inclusion, things work out for us. Here's how. So here's our maximal set Y, and let's look at C and try to bound the chromatic number of C a little bit better. And we can look at a vertex V in the neighbors of A and look at its neighbors in C. And do something similar to before. When we delete these neighbors from C, then C should split up into new components we got after deleting these neighbors and Y. And for each of these little components, the point is we could choose this as C instead, because every vertex here with a neighbor in this new component is complete to it, because being mixed gives us a P5 as usual. So if we look at a vertex V with a neighbor in C, look at its neighbors and delete them, then we could say, if we have a component here, its set of neighbors there could be added to Y to make Y bigger. So why can't we do that? It must be that the chromatic number of this component is too small now. Right. We wanted Y to be a maximal set such that there's a big component complete to it. And here's a little bit we could add to Y to still have a component complete to it, so it mustn't be a big component. So this has chromatic number at most f of k over 2, because that's the threshold we wanted for the chromatic number of C. And so that means that we can prove a bound on the chromatic number of C now by taking a clique in N of A, which we know there's a big one, and then saying for this clique K, the chromatic number of C is at most 12. For each vertex, we proved its non-neighbors have chromatic number at most f of k over 2. So we have k over 2, f of k over 2, 1 f of k over 2 for each vertex of the clique, for the set of its non-neighbors, and then there are the vertices of C that have no non-neighbor in K, but then they also have clique number at most f of k over 2. Right, you kind of see a pattern if we group things by their non-neighbors or we group things by their neighbors. And for cliques of size k over 2, that kind of works nicely because things that are complete to that clique have clique number at most f of k over 2. So what was the point of all this? It's here we can now put things together by saying Here's A, here are its neighbors. And here's the set Y that we picked to make something maximal. Namely, we wanted a component C of chromatic number, at least f of k over 2, which was complete to it. And we wanted Y to be maximal with that property. So what do we know about C? Well, we proved on the previous slide its chromatic number is at most S. What do we know about Y? We know that it's complete to something that has chromatic number more than f of k over 2. So in here, there's a clique of size more than k over 2. So Y has clique number less than k over 2, and this is almost done. And now there's the step where we use what we proved before, because here's a clique of size k over 2, which means that in all of the other components we get from deleting Y, there can't be. We proved that there aren't two cliques of size more than k over 2 with no edges between. So here we have clique number less than k over 2. And if you follow that and believe it, we get this bound on the chromatic number, f of k minus 1 for the neighbors of A, because they're complete to A, so clique number went down by at least 1. And then over here, we actually got the clique number to be at most k over 2 plus 2 times f of k over 2. We get 1 k over 2 for Y, and then we get k over 2 plus 1 for C, and these other components after deleting Y are negligible because we know there's a big clique in C, and so these guys don't have big cliques. And that gives you this recursion. And now you might say, wait, your previous slide had a k here and now it went to k over 2. That seems very much not tight. But somehow it doesn't want to go any further, even though it's not particularly tight. Any recursion we've been able to prove with this proof gives a bound of omega to the log omega. We don't know how to make it better. And the main reason for that is, because we split at k over 2. And we say things are small if they have chromatic number at most f of k over 2. And that, if you look at how we analyze this recursion, doing that is basically not going to give a better recursion. And it's not going to give a better function than omega to the log omega. There may be constants, but it's not polynomial. So this is the P5 proof, and you've now made it through the proof part of the talk. So let me tell you some future questions that are interesting. Well, we would like to do P5, we don't know how. We would like to do forced with no P5, right? We know all trees with no P5, but we don't know all fours with no P5. And so in particular, 2P4, the disjoint union of 2P4s is the smallest open case. But in general, even without proving P5, one might be able to go as far as disjoint unions of double stars. And then in view of Espéray's conjecture that chi-boundedness is the same as polynomial chi-boundedness, there are many exciting classes of graphs where chi-boundedness is known, but polynomial chi-boundedness seems far out of reach, and perhaps the most exciting class of that is odd-hole free graphs, where a hole is an induced cycle of length at least 4. And odd just means odd length. And so Scott and Seymour proved that odd-hole free graphs are chi-bounded by a doubly exponential function. And according to Espéray's conjecture, it should be polynomial. So it would be exciting to even get this to be singly exponential. And, since we can't do P5 and we know Arter-Scheinel when excluding C5, would be natural to get polynomial chi-boundedness for P5, C5, because somehow in view of Arter-Scheinel, that doesn't tell us anything very unexpected. But even in that case, there's a bound. There was previously a bound of 2 to the omega due to Chudnovsky and Seymour, and now we have a bound that's sub-exponential because we know that for P5 free, but there's no way to use C5 currently to make the proof any better. So that seems like a natural next thing to do as well. And I had some questions about chibondedness, but let me instead stop here and say thank you for listening. And if you have questions, please ask.
Yeah, let us thank Sophie for a very nice talk. Questions?
So apart from coloring P5 free graphs, did you get new structural results about those graphs?
No, it would be nice to get. Basically have this proof and it seems to, it gives this bound, and there are many little ways to change it a bit and try to make it a bit better, but none of them actually work out better when you analyze the recursion, and there's no real structure that we used here, right? There's somehow the very non-structural thing of if you have a cut set, you can go one step further back than if you didn't have a cut set, and that's the main tool. But it doesn't tell you anything about what P5 free graphs look like.
Okay, thank you.
Any more questions? Yeah, if not, let us thank Sophie again. Thank you.